All right. Morning, everyone. Welcome to day 21 of Math 133. And today we are going to be looking at the Chapter 9 project. The Chapter 9 project starts on page 569. Most of our projects were in Google Documents, but this one is actually in the course pack. So page 569. If you click on the Chapter 9 project in Canvas, there's not a link to take you to the Google document. Uh, there is a link, though, that we are still going to need that says Random Confidence Level File. And if you click that one, it'll take you to this in StatCrunch, where we have a whole bunch of different confidence levels. 99.8%, 98.7, whatever. Okay. So you'll need to sign in to StatCrunch. Um, you'll also need your data from the Candy project. So you'll want to open that up wherever you saved it, okay? Because we're going to need those numbers for your M&Ms and your Skittles. Um, but the main place that we're going to be entering our answers today is going to be page 569 in your course pack.
Hey,
Um, all right. So, uh, for these, we need four decimal places. All right. So, using the StatCrunch file that we have that has random confidence levels, we want to get three different confidence levels to use for this project. Okay. One's going to be for M&Ms, one's for Skittles, and then one's going to be for revisiting the M&Ms, the sample size stuff. So, what you'll do is you go to data, sample, and then you'll do a sample size of 3, and it'll pick 3 random numbers for you. So over here in StatCrunch, we're going to go to data, sample, and you'll click on sample, data, sample. Select which column the data is in, so it's in confidence levels. So we'll do a sample size of 3. Okay. Um, so what this is doing is just picking 3 random numbers, but uh, this would be a place that you could do random samples. So if you had a population that wasn't small like this one, but if you had a population that was millions of data points and you needed to do a random sample from that, we know that like if you're doing a sample for means, your sample size needs to be at least 30, right? And so you could pick 30 random numbers out of here. But for this, I'm just getting 3 random numbers and it'll put it in a new column for me. So we'll just copy those 86.8, 72.3, and 84.3. Okay. Your numbers are going to be different from mine. Okay, which is good. We want everybody to get a chance to their the project with their own numbers. And your numbers are going to be different for your candy counts as well. Okay. But here's my confidence levels that I got. All right. So part one, M&Ms. Which M&M color had the lowest count in your sample? Fill out the table for that. So my M&Ms, my lowest was red. And so I need to fill in X, N, and P hat. Okay. Uh, First of all, what's N? Lowercase n. Do you remember what that stood for in this class? That's my sample size. That's right. So for me, I had a sample of 145 M&Ms. Okay, all together. 17 of those were red. So my X value here for red is 17. Okay. P hat is X divided by N. So we need to get that. 17, mine was 17 divided by 145. And I get 0.117. Okay. All right. So the proportion in my sample, the proportion that were red was 11%. 11% of my candies were red. Okay. Um, Now, what we're going to do is we're going to use that to take a look at what the proportion of all candies, all M&Ms in the world would be for red. Okay. So, by the way, when we're doing this, we don't always know what that proportion is, but we do for M&Ms, right? So there's six colors, and they make the same. They make the same amount of each color. So 1/6, the true proportion of red M&Ms in the world is 16%, 16.7. Okay. When you're doing a population proportion or mean, you usually don't know what P is. Okay. You don't know what the true proportion is. And that's why we do a sample, because we can't count every single M&M in the world. Okay. So we do P hat instead, and it's an approximation. So I'm saying that 11% of all candies are red, when in reality it's actually 16%. So I'm off, but I expect to be off because I didn't measure every single thing. But is 11% close to 16? Is it not close to 16? Is it close enough? Okay. That's what confidence intervals are going to allow us to do. Okay. We know that we're not going to be perfect because it's a random sample, but we can be 95% accurate. We can be 98% accurate. In this case, I'm going to be using this confidence level. So I'm going to be 86% accurate. I'm 86% confident that the true proportion of red M&Ms is somewhere in this range. Okay. That's the idea behind a confidence interval. Okay. All right. To build a confidence interval, we have to verify that we are satisfying the requirements of the central limit theorem for proportions. Okay. Central limit theorem we talked about in chapter 8, but there were three parts to it. You had to make sure that it was random. We had to make sure that it was independent. And norm. Okay. All right. So first of all, random. Now, we don't have anything in here that says it was random. But we know that the sample that we collected, which was just our bag of M&Ms that we bought, was random because every candy had equal chance of being in my bag, right? We didn't go hand pick the candies and put them into our bag. It was done for us already. And so, they're all mixed together. So, we're going to say that it's random. Now, is it truly random? We would need to know more about the candy, manufacturing process, but we're not going to worry about that. As long as every uh, item in the population has equal chance of getting selected for your sample, then it's good. Okay. Independent. So for independent, we need to check that n times p. Oh, no, that's wrong. We need to check that n is less than 5% of my population. Okay. So you can use either formula if you want to do n is less than 0.05, or you can do 20 times n is less than capital N. So that's the one I'm going to use. 20n is less than capital N. Okay. So my n in this case, mine was 145. Okay. So 20 times 145. How much does that equal? That is 2,900. Okay. Is that less than n? So in this case, what is capital N? N is my sample size. So what's capital N? It's all. So it's the population size. In this case, what is the population? It's all what? Not my total M&Ms in the bag. It's all M&Ms in the world. My bag is just the sample. So I have a sample of 145 candies, 145 M&Ms, which is a representative sample of the population, which is all M&Ms. So are there more than 2,900 M&Ms in the world? Oh yeah, there's way more than that, right? So yes, mine is independent. Okay. Um, very rare that you're going to run into a problem with this one. Okay. I don't think anyone went out and bought billions of candies, right? Hopefully, no one bought 5% of the candies in the in 5% of the M&Ms in the world. You That would not be good. For normal though, we need to check that n times p times q, that has to be greater than 10. Okay. We're going to play a little fast and loose with greater than or equal to. Same thing with less than or less than or equal to. If you got exactly 5%, is it still independent? Technically, yeah. Same thing here. If n times p times q is exactly equal to 10, is that fine? Um, Probably, but for the most part, I'm not going to worry about that. So, my n was 145. Now I don't know p. Okay. Well, okay. I know it's 1/6. Okay. But in practice, in reality, you don't know your p-value. You can get a p hat that approximates it. And so my p hat in this case is 117. My q, thank you, Andrew, is 1 minus that. Okay. So my q is 0.883. Okay. So how much does that equal? 145 times that times that. So 7 times 0.883. And I got 14.9, 14.98, 15. Is that greater than 10? Yes. Okay. Um, Now, if you did this and you got a number that was less than 10, then your answer here would be no. Okay. So did anyone get a no for their uh, normal check here? So n times p times q, did anybody get less than 10? You had more than? Okay. Um, so if you got a no, that's fine. I mean, it's not great. What that means is your results are not going to be as reliable. You're not going to actually truly be 86% confident. Uh, you can't Technically you cannot use the central limit theorem, but we are going to press on with the rest of the project, even if your answer here was no. Okay. If your answer here was no, that means that your sample size was not big enough. Okay. Um, and that can happen. Okay. So, especially if we are looking at a situation where our p-value is very low. Okay. If we were trying to, instead of looking at like M&Ms, if we were looking at uh, we're in the marketing department and we're putting out a new commercial and we want to see if this commercial is better than our previous commercial. Um, we want to be able to, you know, check and see, are people actually buying based on watching this commercial? In that case, our p-value is going to be very, very small, right? Your sample size is going to be how many people see the commercial, and the p-value is going to be how many of them make a purchase based on that commercial. Well, that's probably less than 1%, right? How many commercials do you see each day? You see hundreds of commercials. Do you buy something every time you see a commercial? No, probably not. Okay. You probably don't buy something more than like one based on 1% of the commercials you see. Okay. Um, so in that case, we would need a very large sample size because even if I had, 100 here, or sorry, not 100, even if I had like 1,000 here, 1,000 times 1% is only 10. And then I would need to multiply that by my Q, and that needs to be bigger than 10. So I need a very large sample size for that. Okay. All right. Anyway, moving on. That's it for this page. So even if you got a no there, that's okay. On page 2, regardless of whether or not the requirements were met, let's construct a confidence interval for the proportion of M&Ms that are your color. So I'm using red. Okay, you're going to use whatever color you had the fewest of. Okay. Using our confidence level for number 1. So confidence level that I had was 86.8. Okay, and you're going to have a different one based on what random number you pulled. Okay. Um, all right, so we need to show the formula, the substitution, and the result. So formula, substitution, and the result. All right, so the formula for this is on page 259 in our course pack. The formula for a single population proportion confidence interval is here. And we're going to write out just what says here. Okay. Confidence interval for a sample mean is the one below that. Okay. So we're doing the proportion. So it is p hat plus or minus this crazy thing, z alpha over 2. Z alpha over 2. What the heck is that, right? And then p hat times q hat over n. Okay. All right, that's our formula. All right, so substitution. First of all, we know our p hat. We calculated it on the previous page. Mine was 0.117. That is the point estimate of our confidence interval. And it's basically the center of our confidence interval. It's the middle. Okay. This plus or minus thing over here, this is just a calculation for the margin of error. Okay. So it's basically you take your point estimate p hat plus or minus your margin of error. All right. So my z alpha 2. So I'm going to need to calculate that in a second here. So my p hat, though, I know that 117. So I'm leaving myself some space for my z alpha 2. My q hat is 883. My n is 145. Okay. All right. So my z alpha 2, that I'm going to need to get from StatCrunch. Okay. So to get my Z alpha 2, I'm going to go to Stat, Calculators, Normal. Okay. Am I doing standard or between for this? Between. Yep, that's correct. So for my confidence interval, I'm trying to calculate a lower end and an upper end for my proportion. Okay. So that's why I'm doing a between, because I need a lower end and an upper end. Okay. So it's in between two numbers. Confidence interval is our final answer. Our result is going to be two numbers, a low end and a high end. Okay. So my mean is 0 and 1 because it is a z value. So we're going to leave those alone. Okay. I I don't know what my values here are, but I do know this. This is the percent confidence. It's my confidence level. This I want, in my case, 0.86.8. I want 86% of my data to be in the red area here. Okay. Your confidence interval is going to be wider for a larger confidence. If I'm 99% confidence, 99% confident, that's going to be a much wider area than if I'm only 86% confident. Okay. For 86% confidence, I'm using a Z value of 1.5063. Okay. Now, whatever your confidence interval was, because you did a random sample over here, you did a sample of three. So whatever your first one is, that's what you're going to put right here. Okay. So yours might be 95, 99%. Okay. Or maybe yours is much smaller, like 70%, where your confidence interval is not very wide at all. Okay. All right. So here's what it looks like. So I put my Z value in. Now the alpha over 2, alpha is your error. Alpha is the part where, oh, it's outside that range. Okay. And then alpha over 2 is basically, alpha is the white spaces in here. These two white spaces, those are your alpha. The red area is your confidence interval, your confidence level. Okay. Sometimes we'll talk about alpha, sometimes we'll talk about confidence level. They're very closely related. They just add up to 100%. So, yeah, just be aware of that. Also, we have a lot of proportions, percents, probabilities flying around. Okay. So it can get a little confusing about where I put things. So, for example, I have a p hat. That p is a proportion, it's an approximate proportion of the true proportion. The true proportion of red M&Ms we know is 1/6 or 16%. So there's another percent. And then we have Q, which is another percent. And then we also have alpha, which is a percent. And then we have our confidence level. So basically, the confidence level that we are building is going to be, we are 86% confident that the true proportion is somewhere in this range. Okay. So I realize it can get confusing about all these different proportions and percents flying around. So definitely pay attention to which things go where. Okay. All right. Now that I have this, though, I can put this into Desmos and get my answer. Okay. Um, so let's now, if you do that, you're going to get one answer based on the numbers you have here. Okay. Technically, you'll get a different answer if you use StatCrunch because of rounding. Okay. So you can do it either way. So I'll do a little bit of both today. If I do it in StatCrunch, you'll notice that uh, this this p-value that I calculated was not exactly 0.117. It was actually 11724, blah, blah, blah. And so I rounded it, and that's why you'll get differences. Okay. Anyway, for my case, I'm going to do decimals first. And so I'm going to do 0.117 minus 1.5. Okay, so 0.117 minus 1.5063 times SQRT, 7 times 0.83 divided by 145. Okay. So my lower end for my proportion is 0.077. How many decimal places? 4 decimal places. Okay. So 6, 8. Sure. Okay. If I just change my minus to a plus, I get the other end. I get the upper end. 1, 5, 7, 2. Okay. Oops. That's my pie chart from last time. All right. Where are we? We want the visualizers. All right. Here's my result. So typing all this into decimals, I get this result. This is my confidence interval. I am 86% confident that the true proportion of red M&Ms is between 7% and 15%. Okay. I'm 86% confident with that. Am I 100% confident? No, I'm not. To be 100% confident, you have to check the entire population. You can never be 100% confident. Okay. The whole purpose of a confidence interval is you're not 100% confident. So you're going to give a range of what the true value is because you don't know what the true value is, but you can give a close range. You can say it's somewhere in this area. Okay. Now, is it actually? Is 1/6 in this range? Let's check. Okay. So Willy Wonka claims that the proportion of candies of your color is less than 1/6 of any bag. Does your confidence interval support his claim? So he believes that there's something shady going on at the M&M Corporation, and they're producing less red than they're producing of the other colors. Maybe red dye costs more or something, but he thinks that the true value is not 1/6. Okay. Does our confidence interval support that? Well, that depends on whether 1/6 is in the confidence interval or not. Okay. So 1/6 as a decimal is 16.67% or 0.1667. So for my numbers, is 0.1667 in here? Well, so if I had a number line here, here's 0.07, here's 7%, here's 15%, 16 would be above that. So my confidence interval is here. I am 86% confident that the true value is somewhere in here. And actually, it's not in that range. Okay. So that means that I actually support his claim. My data supports his claim that there's something weird going on and red is produced less than 1/6 of the time. Okay. So I support it because my entire interval, this whole section here, is below 1/6. Now, your numbers might be different. Your numbers might have 0.07 and it goes all the way up to 17%, in which case you disagree with him. He's saying there's something shady going on. You're saying, no, 1/6 is in here. I'm 86% confident that it's somewhere in this range, or your confidence might be higher, like 95%. And so you would say that. So these are the two possible answers for this question. Okay. It can't be above because we specifically chose the one with the least. Okay. If you're checking your red against my red, well, maybe it could be, but so these are the two answers for this question, depending on what numbers you have. Okay. Any questions so far? As always, feel free to stop me as we're going through these questions, okay? Um, but anyway, so did anybody get one did anybody have a does not support? Does anybody have 1/6 in their range? So Andrew actually chose this question, this one. So mine is this, but Andrew's answer is this, okay? So you'll notice that on these projects, when you're using our data, when you're using real data or different data, you might get different answers, okay? So pay attention that when you're working on, in the real world on, at your job on these problems, um, part of the reason why mine 1/6 was outside the range is first of all, I'm only 86% confident. There's a 14% chance that 1/6 is not in, that the true population proportion is not in my range. And in this case, it landed in that 14% chance range that I said that there's a 14% chance that it's outside this range, right? The whole point of a random sample is you cannot measure the whole population. So you can measure the sample and say, well, I'm going to be close. How close? This close. Am I guaranteed to be close enough? No, I'm not. Okay. I probably should have used a larger sample size because a larger sample size means you will be more accurate. Or I probably should have used a larger confidence level. I should have been more like 95% confident or 99% confident. Okay. In my case, I was only 86%. So I left a lot on the table, a lot of chances to be wrong. There's a 14% chance that I'm wrong. That's pretty big, as opposed to like a 5% or a 1% chance. All right, suppose you had used a super big bag with thousands of M&Ms in it. That sounds delicious. But the proportion of your color was still the same as number two, so still 11% for me. The confidence interval created using these numbers would have been narrower or wider. So how do I know this? Okay. So the way I like to remember it is um, a larger sample size is going to lead to your result being more accurate. Okay. That is almost always the case. So if I'd had a larger bag, I would have had a larger sample size, which means I would have been more accurate. More accurate means I would have been looking at a thinner area. Okay. In my case, I had a pretty wide range. Okay. This is an 8% difference between 7% and 15. Okay. So in my case, I would have had, uh, it would have been narrower if your sample size was bigger. Okay. Because sample size and error have a inverse relationship. Okay. And this is the answer for everyone. Okay. Up here, you could have two different answers, but this one, everybody should be circling this guy. Um, By the way, these are relationships that some people might struggle with, so it's definitely a good idea to study those for the final exam. Okay. And we'll talk more about them as we go. Okay. So if you're still not sure how that worked, the main thing is larger, larger sample size equals more accurate. That's how I remember it. Okay. The width of your the width of your um margin, the width of your confidence interval is based on your margin of error. The width of your confidence interval tells you how accurate you are. If I said that um, I'm 99% confident that the average height of the people in the US is somewhere between 3 feet tall and 8 feet tall, that's a huge range. Someone who's 3 feet tall is tiny. Someone who's 8 feet tall is a giant. Okay, that's way too big. Okay, so if I wanted to be more accurate, I would want a smaller range, a smaller confidence interval. Okay, good. Let's move on to Skittles. Part two, confidence interval with Skittles. So which Skittle color had the highest count in my sample? Okay. I don't remember, so I'm gonna go look. For Skittles, my highest was yellow. Oh, that's the worst color. And I had the most of those?
I
Okay.
disagree.
Elaine likes the yellow ones. Oh man, Elaine, you let me down. My sample size was 241. Uh, my X value, I had 55 yellow. So my P value is 55 for 241, which is 0 point something. 0.228. Okay. Now yours obviously is going to be different from mine depending on what numbers you had. Um, and we're going to use this as an approximation for the p-value of yellow in all Skittles. Now, normally, like I said before, we don't normally know what the true proportion is. We can only estimate it. We can say, well, it's somewhere around 22%. How close is it to 22%? Well, I can say I'm 86% accurate. Or in this case, we're going to use the confidence level for number two. So my confidence level was for number two was 72%. So I'm going to say I'm 72% accurate that it's somewhere in this range. And that's what the confidence interval is. It's just giving you that range where you think the true proportion is. It's somewhere in this area. Okay. But we've seen already that sometimes you're off. If you're 72% accurate, 72% confident means you're 28% not confident. There's the 28% chance that you're going to be wrong and that it's actually outside that range. Okay. So 72% is probably a pretty terrible confidence level. A normal confidence level for, a business case, if we were looking at like making a business decision, um, at your job or whatever, uh, we would be looking at somewhere like 95%. 95% is kind of the rule of thumb. 95%, 99%. There are some times that you can make the right business decision even if you're 90% accurate, but I don't really feel comfortable going below 90%. So, 99.97%, or sorry, 99.7%, 99.7, we remember that was the confidence level for 3 standard deviations from the mean. So if you want to get real accurate, you would do it at that level. Um, Sometimes it's very rare, but there are times where you need to get even more accurate than that, if we're talking about medical cases, things like that, but usually not. Usually that's good enough. Verify all the requirements for constructing a confidence interval for the proportion are satisfied. So again, check if it's random, independent, independent, and normal. Okay. Random, yes, because every Skittle had equal chance being in my sample, right? In this case, my sample was my bag of candies I bought, right? So So we can't say yes given because I don't actually, it's not given that it's truly random. So but this is good enough. Independent. For independent, we need to check 20n is less than capital N. Okay. So 20 times your sample size. Mine was 241. Is that less than capital N? So mine, I have 4820. And sample here is the number of Skittles in the world. So is 4,820, is that less than the number of Skittles in the world? Oh, yeah, it's way less, right? Absolutely. So we definitely have that. Nobody went and bought 5% of the Skittles in the world. Nobody's that rich. Normal. For normal, we need to check that N times P times Q is greater than 10. Okay, so my N is 241. My P hat is 0.228. And Q is 1 minus that, which is 0.772. Okay. I can do that in my head. I can't do this in my head. So I'm going to come over here and do 241 times 0.228 times 0.772. And that is 42.4. And that is definitely bigger than 10. So, yes. Okay. So I'm good there. Okay. So 3 yeses means that we can build a confidence interval using the central limit theorem, using our formulas on page 259. Regardless of whether or not the requirements were met, construct a confidence interval for the proportion of Skittles that were your color. Mine was yellow. We need to show the formula. Substitute in the numbers there. And show our result. All right. Our result, just like last time, will be 2 numbers, a low end and a high end. Okay. Formula for this. P hat plus or minus Z alpha over 2, big old square root, P hat times Q hat over N. All right. And again, that's page 259. Same formula, right? We're doing the exact same thing, except just plugging in different numbers. My Z alpha 2, I want to use the confidence level number 2. So on your page 1, you selected 3 confidence levels. I did 86% for my M&Ms. I'm going to do 72% for my Skittles. Okay. That's fine. So back over here to get my Z alpha over 2, I do between, and we put in our confidence level, 0.72.3. Oh, not 0.723. There we go. Compute, and my Z alpha over 2 is 1.0871. Now, I have a negative 1.078 and a positive 1.078. That's why it's a plus or minus. So I have a positive one and I have a negative one. Okay. Because basically, on my number line here, right here is 0.228. That is the middle of my confidence interval. I'm going to need to go up and down from that to get my high end and my low end. Okay. And I'm 72% confident that the true value will land somewhere in this range. What is the true value, by the way? So uh, there's five colors in Skittles. So 1 out of 5. What is 1/5 as a percent? Does anybody know? Can you guys tell me what that is? 1/5 as a percent, please. 70%, yeah. So the true population proportion is 20%. Now, again, you don't usually know that, okay? If you knew it already, then there's no point in doing the sample, okay? The whole point of doing the sample is you don't know that proportion value and you're trying to find it, okay? Like if I wanted to know, um, you know, what percent of Americans have AIDS, okay? I don't know that number for sure, okay? But I can use a sample to get an approximation, okay, of what the true proportion is. All right, so and that's an important number for medical stuff. Obviously, what percent are yellow Skittles? It's a little less important, but it's fine. So we already showed how to do that in Desmos. We're gonna do it this time in StatCrunch. Okay. All right, so to do it in StatCrunch, you have to give me a second because I don't remember the exact. Let's see. Help me out, Elaine. Do you remember which ones it was? It was proportion stats, one sample with summary,
Yeah.
number of successes. I had 55 yellow out of 241 sample size. Click the button for confidence level. Change this to, I want 72% and compute. It gives me this. So my result here is my lower limit, which is 0.1988. My upper limit is 0.2576. Okay. Using my upper limit and my lower limit here. Okay. Again, that was proportion stats, one sample with summary. Okay. So my result is 0.19 and 0.25. That's my upper end and lower end. Okay. You don't need to draw a number line. You don't need to draw this. This is just, I like to be visual. So this was just to explain what the heck we're doing. Willy Wonka is back. He's bothering us again. Uh, claims that the proportion of candies of your chosen color is more than 20% for any bag. Does your confidence interval support his claim? Well, 20% in my case is here, 0.20. So in my case, 20% is in my confidence interval. I am 72% confident that the proportion of yellow Skittles is somewhere between 19% and 25%, and I'm correct. In this case, I was 72% confident and I was accurate because 20% is in that range. So I disagree with you. I disagree with Willy Wonka. Willy Wonka is saying that there's something weird going on at the Skittle Company and they're making more yellow. That was what I thought, right? I was like, I don't like yellow. I think they're making more than they should. Um, but no, I'm 72% confident that actually they are making 20%. So if you if 20% was not in your range, if it was here, then this would be your answer. So these are the two possible answers in this case, because if 20% is here, then your entire interval is above 20. Okay. So those are your two possible answers there. All right. Question 11. Suppose when creating the confidence interval for number 9, instead of using the confidence level number 2, you had used confidence level number 1. Confidence interval that you created would be what? Well, let me go back and look at those. So on the first page, you selected a confidence level and another confidence. In my case, this one is a higher confidence than this one. So in my case, I was more confident with the M&Ms and less confident with the Skittles. Okay. So in my case, if I had, instead of using 72% here, if I had used 86%, okay, my confidence interval would have been wider. Okay. It would have been wider because the confidence level and the error have a direct relationship. Okay. If I had been more confident, then that means I would have had to look at a wider range. Think about it like this. If I wanted to know with 100% accuracy what range my true proportion would be, I would have to look at everything. I'd have to look at the entire number line, okay? Because if I wanted to know it with 100% 100% accuracy, I would have to check every single thing, okay? So that would mean I'd have a much wider range, okay? If another way you can look at it is if you put a bigger number in here, 99%, your red area is very wide. The red area represents your confidence interval. If you put a very small number in here, like 70%, it's much thinner, okay? So this is my answer, and that was because this number is bigger than this one, okay? If these had been flipped, and let's say that this one was 70% and this one was 90%, okay, then when I built my confidence interval number 2, it would have been narrower, okay? So it depends on what numbers you had here. If this number is small and this number is large, then it's this one, okay? It's narrower. Moving on to our last page. Calculate the minimum bag size, number of candies required to ensure that the proportion of your color of M&Ms, M&Ms, I was looking at red, is within 2% of the true population proportion for that color. Use confidence level number 3. So now we're using this one, okay? And assume you do not have a prior estimate for the proportion. Show the formula, the substitution, and the result. Okay. So let's say that I had done this and I wasn't happy with the results. And in this case I wasn't, right? Because for my question uh number 4, I said that it was this range, but actually the true proportion was outside of that. Okay. So I'm not happy with the result. So I want to redo this experiment. Remember that a larger sample size means you will be more accurate. So I say, okay, I need to be more accurate. How big of a sample size do I need? That's a very important question for any kind of research study. How much do I need to sample? Because when you have a large sample, it is more expensive, whether it's time, whether it's actual dollar costs, whether it's, amount of people helping. So if I wanted to do uh, a uh, a test to see you know, how successful this new commercial this that I'm putting out, because I've spent lots of money on this commercial. I want to make sure that it's good. If I want to figure out if it's going to be successful, like I need to do a very large test that's going to take a lot of time and it's going to be expensive. Okay. Versus if I just show it to like 100 people, that's going to be much easier, but it's going to be much less accurate. Okay. So calculating your sample size is an important step. You'll find the formulas for that on page 261 in our course pack. And there's two of them, depending on whether you're looking at sample size for proportions or means. And I've said this before, so there's a lot of similarities depending on whether you're looking at a proportion or a mean. Um, and so that's why we kind of cover them all together at the same time. Today, we're very focused on the proportion side, but yeah, pay attention on, the chapter 9 review and the cumulative review and the final exam. Are we looking at proportions or are we looking at means? It'll usually be obvious. Okay. There's actually two, even if you're looking at proportions, there's two different ones, depending on whether you have a prior estimate or no prior estimate. Okay. So, like, for example, if I wanted to know, you know, uh, what percent, let's go back to what I said earlier. What percent of the people in the US have AIDS? Um, does anyone have a guess? I have no idea, right? Maybe you know, but I don't have a good guess on that. And so I would go with no prior estimate. Okay. On the other hand, if you have done this experiment once before, which we did, okay, um, you can just use your previous guess of what the proportion was. Okay. But for this one, we're going to assume that we don't have a prior estimate. So our formula for this one is n equals 0.25 z alpha over 2 divided by our error squared. It's this one. We use this one if we don't have a prior estimate, and that's what they're asking here. We do not for this one, okay? I know we do. We're just going to say we don't, okay? So substitution, n equals 0.25. Calculate our z alpha over 2 and our error. Our error in this case is 2%. We want to be within 2%. So the true value is 16%. So we want our actual um, uh, answer to be somewhere between 14% and 18%. Okay. Z alpha over 2, we are going to use the confidence level for number 3 to calculate that. So mine is 84.3. So I'm going to put that right here. Confidence level 84.3. My Z value is 1.4152. All right, great. And square. Don't forget the square. There we go. All right, so my result is going to be decimals here. 0.25 times parenthesis 1.44152 divided by 0.02. Close my parenthesis. If you hit the shift button and the 6, it'll let you square that. Oh, nope. I want to close my parenthesis here. And I want to square the whole thing. There we go. All right. So that gives me 1251.74. So if I want to be that accurate, I'm going to round that because um, you can't actually get a bag of candy of M&Ms that is 1,251.7. We don't count point 0.7, right? You either have a whole candy or not. So I will round that up. Okay. And if this was 0.34, I would still round up. We're always going to want to round these up. Okay. All right. Suppose when computing number 14, you had used a 1% margin of error. So that means my error is smaller. That means I'm more confident. I'm more accurate. Okay. To be more accurate, you need a larger sample size. Okay. In my case, I'm looking at a 2% error, so somewhere between 14 and 18%, with 16 in the middle. If I want a 1%, if the true value is 16, a 1% is from 15 to 17, so it's narrower. So I need to be more accurate, I need a larger sample size. Okay. Lastly, calculate the minimum bag size again, this time with the same confidence and error, but this time use your p hat from number one. So my p hat from number one was this. So we did have a prior estimate. Okay. So there wasn't any reason why we did this. We should have just used the p hat that we had before. So if you've done this study already, then you have a previous result and you can use that for help in calculating your sample size. So to do it, you need this guy. P hat, Q hat. It's very similar, except instead of the 0.25, you put your P hat and your Q hat out front. P hat, Q hat. Still got Zelf over 2, still got our error, still squared. So same error. And the same Z alpha over 2, actually, so that's nice. I don't have to calculate that again. So whatever confidence level your number 3 was, that's going to correspond to a Z alpha over 2. So plug all that in, see what we get. So I'm just going to change this to 117 times 0.883, and I get 517.28. And we are going to round that up. Even though normally we would round this down, we're going to round that up. Okay. Okay. Round it up to the nearest whole number. Of the three confidence levels, these are the three that I had. Which would yield the largest sample size? Largest sample size is the most accurate one. So for me, so you're going to circle whichever of these numbers is the highest, because a larger sample size means you are more confident, you're more accurate, better results. Okay. All right. That's it for project 9. So uh thanks for sticking around and a few extra minutes. I apologize for that. Uh and I will talk to you guys on Thursday. Oh, sorry. It is Thursday. Oh, have a good weekend. We'll talk to you on Tuesday.